that how the charts occurrences we get in nature and how the chart is formed. That is the fundamental, that how the chart is formed and how it occurs in the nature. What is the source of silica? This is the another issue. So source of silica, if we see the major source of silica, that is the continental weathering reaction. Continental weathering reaction. And what we discussed when we started this sedimentology course, that all the reactions of weathering, where the carbon dioxide and water, these two react with feldspar, then you basically release the silicic acid, SiO-OH. You remember those reactions? You people remember those reactions, or should I write it? Hello?
Yes, sir. Please.
Hello. Yeah. So KLSI3OH plus CO2 plus H2. So you get Al2 Si2O5OH4, that is called kaolinite. You get SiO-OH4. You read plus K2CO3. This is the reaction. So you always release the silicic acid. Now this silicic acid is the primary source of silica when you get the deposition of chart in a sedimentary basin. This is the primary source. That weathering reaction that basically releases the silica from the mineral structure in the form of silicic acid. This is number one. That is the source of silica. Number two, it is the volcanic output. Volcanic output. I'll put a figure and then I will explain. Volcanic output, that you get the siliceous solution that are coming from the volcano. And the hydrothermal solution, the siliceous hydrothermal solution, that is a major thing. We also get some the silica that basically is a pore water reflux. Some of the silica that is actually supplied to the nature, to the basin in forms of the pore water reflux. So if I draw this figure, then it will be little clear to you. entire figure?
No, sir, not the lower part.
Okay, you first draw the upper part, then I will change the screen and you will see that. Please let me know when you require that. If you have problem in reading any word, please let me know.
Sir, after pour water, what is written?
Pour water reflux. Pour water reflux.
Okay, sir.
I am now changing the screen to see the lower part. Okay. It is visible now.
Yes.
Please let me know when it is done. Mega quartz. I believe it is done now. Now, very carefully look at this diagram. There are two parts of the diagram. One is this part, another is this part. Okay? What message is being given by this diagram? First message is that what are the sources of silica? As I discussed, one of the major source that is this. What is the continental weathering? Continental weathering. And this is a major source of silica in the basin. Then it is a volcanic output. This is the volcanic output. This is another source of silica. And the third source, what I talked about, that is the pore water reflux. Pore water reflux. That means silica solution in the pore water, it becomes more concentrated and it is refluxing within the basin. How it becomes concentrated, I will discuss that. And when it reflux means that it is going back to the basin, then it also supplies some amount of. Sometimes some anaerobic dissolution of the siliceous class that also supplies, but their volume and contribution is very, very minimum. The major contributor are number 1, the continental weathering, number 2, the volcanic, and number 3, the pore water reflux. These are the major contributors of the silica in the basin. Now, next, so what is the other thing that is written here? It is you can organic scavenging, organic death and settlement. All these they are related to the organism. I am discussing everything related to organism. Why I am not calling anything inorganic precipitation? I am not writing anything called inorganic precipitation. Inorganic precipitation may leak in era. I am not. I am always writing the organic scavenging. Right? This issue I will come after describing this figure. That why I am not writing inorganic, why I am always writing that it is organic. That means, what is organic scavenging? That the organisms, they are scavenging the silica from the water column and making them their taste. What are those organisms? Number one, diatom. Number two, radiolarian. Number three, there are the spicules. Spicules. These are the major. What is radiolaria? It is a marine planktonic protozoa. What they do? They make their taste. They make their taste by sea. And where? In the deeper part of the ocean. Deeper part of the ocean. And then these organisms, they after their death, they get sick. They get sick. In the shallow diagenesis, these organic taste, they go into dissolution and increase the concentration of silica in the pore water. From that pore water, then the diagenetic pathway starts. So, what is there any question here till now? Okay. If there is no question, then I am basically forwarding. I am now coming to this question why I am not calling a inorganic precipitation. This part I will be discussing separately. Now, first of all, that what is the average silica concentration in riverine water? And what is the average silica concentration in marine water? Let us see that. The average concentration of silica in riverine water, it is only from 10 to 15, maximum 20 ppm. 15 ppm. That is in the fresh water. Okay. In case of marine water, in marine water, average silica percentage is 1 ppm. If you see the solubility of quartz in marine water, that is in 11 ppm. That is the solubility of quartz. That means, what does it mean? That means that if you have the silica content in marine water less than 11 ppm, then the quartz will go into solution. You are understanding what I am saying?
Yes, sir.
That means for a quartz to be stable in marine water, you require at least 11 ppm silica. But average silica concentration in marine water is 1 ppm. If you come to amorphous silica, then it is 116 ppm. Amorphous silica stable हो ही नहीं सकता unless you have a silica concentration in marine water 116 ppm. So what is the meaning of that? Meaning is seawater is largely silica undersaturated. Seawater is largely silica undersaturated. Then the question is, if it is undersaturated, who is removing the silica? In the river water, you have 15 ppm silica, and that river water is supplied to the ocean. And now in the ocean, it is becoming 1 ppm. That means somebody or something is removing silica from the ocean water, and that's why it is becoming less in silica. Now, what is that? What is removing the silica? Then the question comes that what is removing the silica? I think the problem is clear to you.
Yes, sir.
Is the problem clear to you? Okay. If there is any confusion, anybody, he or she may ask me that what exactly the question I am trying to pose. I repeat that the river water has 15 ppm C. But when it comes to ocean water, it becomes 1 ppm. And if we experimentally see what is the minimum concentration level required for the stability of quartz or amorphous silica, then we are getting it is about 11 ppm or 160. So the conclusion is that the quartz and amorphous silica are not stable in the marine water. This is number one. But we get quartz. We get silica deposit as a basinal deposit. We get. It is not that we do not get. We get. That is why it is a problem. That ocean water is 1 ppm, not stable or saturated with respect to quartz. But even then, we get the silica deposit. And that silica deposit we are getting right from Picambian to the dust. How? How this is found? Who is removing silica from it? That is by these organisms which are making their taste by silica. And that I have already discussed, the diatom, radiolaria, the spicutes, siliceous spicutes. They are actually scavenging silica from the ocean water, making the ocean water undersaturated with respect to silica. Now you can say the organism is making their taste, and then they are living in the same water which is undersaturated. In that case, their taste will go into dissolution. Isn't it? Isn't it? Yeah. So they are making their taste and scavenging silica, making the water undersaturated, and that undersaturated water will dissolve their taste. But that is not happening. Why? Because these organisms, they basically protect their shell by a metallic sheath. Metallic sheath. And that metallic sheath protect their taste from the wrath of undersaturated marine water. They scavenge silica, and as they make their taste, at the same time, they also grow a metallic sheath, SHEATH. That is a layer of metallic sheath that is protect their taste from the wrath of the marine. Now, what happens when these organisms, they die and they settle on the bottom of the ocean? Then their metallic sheath that get decomposed because no vital factor that is operating there. no life is present there. So then their taste, they come into the wrath of the pore water. Pore water is nothing but the water, that is the sea water, trapped within the pores of sediment. Now these organisms, suppose there are diatoms, there are radiolaria, there are diatom, spicules. Now their metallic shade is removed, and their taste, they are coming in the contact of the pore, and the pore water is undersaturated. So what will this pore water will do? It will then dissolve this taste. They will dissolve this taste. And as these tastes are dissolved, then the concentration of Si in this pore water, that becomes saturated to oversaturated. And this, from this saturated to, so that if you remember the diagram I had drawn, that in the diagram in the lower part, I have said that it is a saturated pore water. From there, the siliceous solution that is formed. From this saturated to oversaturated siliceous solution, the first precipitation what we get is not quartz but opal A. Opal A, which is a metastable quartz form, which is not stable quartz form, which is a metastable quartz form, cryptocrystalline metastable form. This opal A, then further diagenesis, it changes to opal CT, which becomes more needle shaped, and from the amorphous fluffy form, it becomes the needle shape and the sheath shape, opalcity. This opalcity then change to microquartz, and that microquartz gives rise to metaquartz. This is one line. This is one line that I have drawn. The other line is that these silica, these may participate in the different siliceous mineral, the silicate mineral formation. That if you have the presence of the aluminium with that, presence of the cations and anions, then there are different kinds of siliceous minerals that may also be because of the availability of the silica. So two lines. But if I concentrate on the chart and the quartz line, then the change is opal A to opal CT to microquartz. Okay? Now, this is one. Now I come on to, yes.
Sir, opal A is cryptocrystalline metastable. क्या था पूरा sir?
It is cryptocrystalline, fine grain cryptocrystalline, fluffy.
Okay, sir.
FLU double A coil and metastable. Then the opal CT, it is actually needle shape or sheath-like, SHEATH, sheath-like. These are all metastable forms of silica precipitation, but the stable form is the microquartz and the megaquartz. Actually, if you see that no opal A or opal CT we get for the chart deposit more than 60 million. Opal A, opal CT, that is preserved only in some rare pockets up to 60 million year chart deposit. The older than 60 million year, no opal A, opal CT, they are metastable, they all change to the microquartz and the metal. Okay. Now I come on to the problem of inorganic precipitation of silica. Inorganic precipitation of silica में problem क्या? What are the problems in the inorganic precipitation of silica? So what people have observed that the solubility and the upwards, it is a function of both pH and temperature. pH and temperature. I draw two figures, then I will explain. This is the relation with respect to pH. You can draw the figure. Have you drawn it?
Sir, what is written on the y-axis?
Silica concentration in ppm, and on this side is pH. This is the solubility curve. This is the solubility curve of silica with respect to pH. What we are observing, that up to pH 9, starting from pH 2, which is highly acidic, and up to pH 9, the solubility is not very high, but the solubility drastically increases once you cross the pH 9. Am I clear? Hello?
Yes, sir.
Yeah. What does this mean? What is the pH of the ocean water? What is pH of ocean water? 7.5 to 8.3. Average is 8.3 to 8.3. Now ocean water is a mildly alkaline solution. And if you make the solution more alkaline, then the silica will go into dissolution very fast. But from 5, 6 to 8.5, this pH, the silica is not going to the dissolution so fast. Am I clear? What is 2 to 8, 7.58, this solution? These are acidic solutions. Neutral is 7.5 minus logarithm of hydrogen ion concentration. So what does it mean? That the silica is less soluble when you have a mild to strong acidic solution, but it goes into the extensive dissolution in the alkaline solution. Now you see the distribution in the ocean. Where you get the siliceous taste? Below the CCD. Hello? Below the CCD, radiolarian chart, diatomaceous earth, they are below the CCD at the deeper ocean. They are not in the shallow ocean. Now, what is happening in the deeper ocean? Because of more and more higher pressure, lower temperature, more and more dissolution of the CO2, the ocean water in the deeper part is mildly acidic. Whereas the shallow part of the ocean, they are more alkaline. Now all the carbonaceous, whatever the organism they make their taste, for them the acidic condition is very, very detrimental. They cannot go to deep ocean. They always try to be in the alkaline ocean, in the shallow part, and live there happily with their taste not getting dissolved. Just reverse is those organisms which make their taste by the silica. For them, the alkaline condition is not very good, but a mild acidic condition, that is very good, because they are not going into dissolution very fast. See the beauty. And they are basically forming the radiolarian chart, and this we get the radiolarian chart associated with ophiolite sequence. Why? Because those radiolarian charts, they are basically resting on the oceanic crust. Is it clear or not? Is there any question? Hello?
So please repeat once more.
What I am saying from this diagram, that from below 8.59 pH, the solubility of silica is low. That means silica do not go into solution. Their solubility is low. But once you cross the 8.5 to 9 pH, then the solubility drastically increases. So this observation, if I extend it to the marine condition, then in a marine condition, this I have discussed in detail when I was discussing carbonate, that why there is a CCD? Because the seawater become more acidic with more and more dissolution of carbon dioxide, atmospheric carbon dioxide, because of lower temperature and higher pressure. Now, if it is the deeper water is more acidic, that is more good for the siliceous organism, but not for the carbonate organisms which make their taste by carbonate. Suppose the pelicipode, gastropode, they all make their taste by the carbon. Whereas the radiolaria, they make their taste by the silica. And they see beautiful, they are bathymetric distribution. These carbonate bearing organisms, they do not go to the deeper part because that is not good for them. Their taste will go into dissolution. But the siliceous organism, they will not come to the shallower part because their taste is made up of silica and alkaline solution is not good for them. Am I clear? Is it understandable?
Yes, sir.
Now I come on to another. That is, what is the relation with the temperature?
Done, sir.
Okay. So this is a temperature versus concentration curve. One is for the amorphous silica, another is for quartz. So what we are seeing that the solubility increases with temperature. Actually, what people have observed that the solubility of quartz at 100 degrees centigrade, it is about 3 times than the solubility at 25 degrees centigrade and 1 atmospheric pressure. If I have the 1 atmospheric pressure, then the solubility of silica increases 3-fold if I increase temperature from 25 degrees centigrade to 100 degrees centigrade. So with respect to temperature also, the solubility increases. So 2 things I have discussed, that the solubility increases with respect to temperature, solubility increases after the pH of 9. And these two actually do not allow the large scale inorganic precipitation of silica. Inorganic precipitation of silica, that is because I tell you, the major cause of course is the marine water pH. Marine water pH is an alkaline pH because it helps the carbonates. Carbonate bearing organism, they are help. So the alkaline pH is not at all suitable for the precipitation of inorganic precipitation of silica. Rather, what happens that the diatom radiolaria, they scavenge the silica from the undersaturated, from the marine water and make the water, marine water undersaturated in respect to silica. Okay? Now, what are the different ways we get the silica? In nature, how the silica we get in nature. Number 1, you can have bedded silica, bedded. Thin beds of silica alternating with shell. That you can have. The beds can be of different thickness. Bedded silica. Number 2, nodular silica, nodular. Number 3, massive chart deposit. Number 4, chart without any organic signature. 4 different types.
Sir, please adjust the screen. The upper portion is not visible. Sir, okay.
Now, bedded, that is thin beds of silica alternating with shell. alternatively. 3 beds of silica alternatively. Then people tried to observe how these thin beds are formed. What they found that in many of the thin beds, they are finding the organic trace, that is diatom or the radiolaria. These tests are there, and what happens that when the tests they are going into dissolution, and in their place the saturated silica solution is precipitating the opale or opacity, and that is changing to the quartz. So it is going to dissolution and recrystallized. So either organic taste, or they are recrystallized product. It is same in case of nodular or some massive charge. I am particularly talking about the phanerozoic charge. I will come to the Precambrian charge after that. Now, nodular charts, there you get that there are nodules, chart nodules, but they are not joined. Chart nodules, they are not joined. Or there is a massive occurrence of the chart. Everywhere, in many of the phanerozoic charts, people have shown that they are actually derived from the organic tastes. They could get some remains of the organic taste, or the organic taste has been totally recrystallized in the form of the opale, opacity, and the micro and melanoma. Okay? But there are charts also where no organic signature is found. And those are mostly the Precambrian charts. And that is an enigma, that how these charts, because we are largely discarding the inorganic precipitation of silica. So if we discard the inorganic precipitation of silica, then how the charts without any organic signature they are doing? And that is an enigma. In some of the Precambrian charts, there are thick bedded charts. There people have shown the presence of some cyanobacteria. Now, whether cyanobacteria that help in the chart formation, that is a question. That is not yet experimentally proved. But some people have reported the cyanobacteria. How much organic influence was there in the Precambrian chart? That is a question and not yet resolved. Okay. Now, Precambrian chart is actually a problem, but it becomes a very good proxy for understanding the Precambrian seawater temperature. The chart is very good proxy for Precambrian seawater temperature. Is there any question here? Can you see the figure?
Yes.
Can you read all the text? Hello.
Yes, sir.
Yes.
Okay. So have you drawn it? Can I start?
Yes, sir.
So if you see this figure actually trying to tell you all the different ways of chart formation. Okay. What is at the top of this figure? That it is talking about the siliceous organism or siliceous seawater. Whether it is a inorganic precipitation or it is a scavenging of silica from the seawater, all those that has been taken care of. Because we have to interpret both phanerozoic and Precambrian chart. And the Precambrian chart do not have the advantage of this organism effect. So how all the Precambrian and phanerozoic chart together, how we can represent it in a single figure for the entire development of the chart. Here, what you are seeing, that's why the seawater inorganic and the organic, both the effect that has been taken care of. Now this is pore water effect that has been shown. So so what we have seen that in the Precambrian chart we do not get much in signature for the organism. We get some cyanobacteria, but its role is not yet fully proved. So if we believe the Precambrian chart is an inorganic precipitation, then the Precambrian chart definitely would have taken a path which is actually reflected by sea, where not much of diagenetic role is there. Directly from the seawater it is getting precipitated as a microclimate. So that may have followed this path, which may be the Precambrian chart. So Precambrian chart. But if you come to the phanerozoic chart, then it is more of the organic effect. That is for sure, because we have seen that. And even the modern world, modern ocean, we have the radiolaria diatom. How we know how they make their test. So they basically go to the diagenetic path. And that diagenetic path is opal A to opal city transition, opal city, then opal city to microquark transition, microquark, and then megaquark. So they either take this path or take this path or take this path. So any path they can share. And that is the total diagenetic path where opal A to opal city to microquark to megaquark, all these transformations that gets. Is the figure understandable to you?
Yes, sir.
Okay. So this is a figure that basically tries to show you that either in the diagenetic pathway or through the direct precipitation from the seawater, that is depending upon that whether it is a Precambrian chart or a phanerozoic chart, that how much the organic effect, and that is basically taken care of in a holistic diagram to show that how the chart that gets.
Sir,
Yes.
sir, please explain the Precambrian chart sea path again.
Yeah. So what is the problem in Precambrian chart? The problem in Precambrian chart is that you have, suppose I do not know, there is a huge chart deposit in the Bijawar basin, which is called Malera chart, and is a thick, tens of meter to hundreds of meter thick chart deposit. How you can account for this thick chart deposit? That also in the paleopathologic time. There is no known siliceous organism at that time. But the chart, because I discussed that the modern sea, that is the undersaturated with respect to silica and do not promote the inorganic precipitation. Then how I can account for this Precambrian chart? So people then tried, is there any other type of organism that contributed the chart? So some people showed that there is some cyanobacterial effect. But whether cyanobacteria can scavenge silica and help in the silica precipitation, that is not experimentally proven. So, as of now, that many people believe that the Precambrian chart, possibly there was a situation because it was a more acidic ocean, because of higher carbon dioxide pressure in the atmosphere, and that interaction of the atmosphere and the hydrosphere and more exchange of carbon dioxide, what present day ocean, it makes more exchange of oxygen. The Precambrian ocean used to make more exchange of the carbon dioxide. So the Precambrian ocean would have been more acidic, and that acidic condition possibly promoted the precipitation of the silica. That many people do. And that is why that if there is a direct precipitation of silica, then there is no question of the requirement that you have the scavenging of silica from the seawater, then you go to dissolution, then in your place the microquark that is recrystallized. So all this diagenetic pathway which is required for the phanerozoic chart to explain the bedded chart or the nodular chart, that requirement is not there for the figure. You can directly think of the inorganic precipitation. And that is why it has been reflected by the path C in this figure, where there is no major diagenetic path of the opal A, opal city, but a direct change from the seawater to the microquark.
Okay, sir. Thank you.
So this is actually there are many of the questions which still remain unanswered, and that is why because Precambrian chart that has been modeled by inorganic precipitation, that is why people believe that chart can give me a very good indication that what was the temperature, because as you know, the temperature, if you increase, that silica solubility increases. So if chart is getting precipitated, definitely the temperature, Archean ocean, the average temperature of Archean ocean, that is basically people believe that Archean ocean had a temperature more than 70 degrees centigrade. But the surface ocean in the modern surface ocean, it is about 28 degrees, 25 to 28 degrees centigrade. So the question, what was the temperature of the Archean or Proterozoic ocean? That is a big question. And that people try to answer from the chart deposit by the couple isotopic study of oxygen and silica. Oxygen 18 and silica 30. These two isotopic couple isotope, India में होता नहीं है. Only IIT Kharagpur is trying a little bit. People go abroad to do this study, couple isotope of oxygen and silica, that people are trying to use it, the Precambrian chart, to identify that what was the Precambrian seawater table. Is it okay? Hello.
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay. So with this, I end the chart discussion. Hope you people could understand that what are the problems in chart, and जो हम लोग field में देखते हैं that quartz vein, chart, and we neglect that. But chart is a big problem in geology, and though we do not give much importance, the major reason that we don't understand it properly. That's why we do not give any importance. Okay.
Hello? Sir?
Yes. Yes. Hello.
Hello?
Please.
Sir? Sir, Pritam, sir.
Hello.
Hello?
Yes.
Sir, I have one just little confusion or a question like that. That the solubility of silica is a function of this pH and temperature. So, is there any possibility both this function is working together, or they are working as separately?
Yeah, those can, we do not know. In Precambrian, they can be operating together also. We do not know.
Okay.
We do not know the temperature of the Precambrian ocean. We do not know the pH of the Precambrian ocean. And there can be that both the functions, they are equally operative, but one is actually overriding the other. All these possibilities are there in the Precambrian. Who knows? There is that is what people are doing active research on chart in the entire world. They are trying to do the coupled isotope analysis of chart and trying to reach out to what was the temperature condition of the water column and what is the pH condition. So all these, there are the active studies going on in the inquiry. And unfortunately, no study in India.
Okay.
There is some attempt are being made in IIT Kharagpur. I know one student is trying to do his PhD on chart, and they are trying to establish, but there is no other known knowledge of the chart people have worked on.
Okay.
So the last topic in our course, I am coming to that. That is tectonics and sedimentation. Today I will just introduce the tectonics and sedimentation. Tomorrow I will be discussing it. Now tectonics and sedimentation. You see, first we know that the sedimentary basin, if I describe the sedimentary basin, it is a depression in the earth crust that can host a thick pile of sedimentary sediment. That is what is a sedimentary basin. Now the question that how a sedimentary basin is formed, how it is getting filled, how it has gone for the question. It is a big question. How a several kilometer thick sediment succession that is being accounted for in a deposit Suppose you think of your Vindhyan Basin, about 4 kilometer thick sediment package. Now it is actually compacted and consolidated. Think of when it was not compacted and unconsolidated. Then it would have been a 10 kilometer thick sediment package. Forget about that. Think of Shivali. Think of the present Gangetic alluvium, and if you drill in the Gangetic alluvium, what is the thickness of the Gangetic alluvium? So, what is a sedimentary basin? It is a depression. Now, how this depression is formed, and how with this depression it gains its depth, and what makes this depression to preserve several kilometers of the thickness of sediment? How it is? If I say if I see the present day basin, what is the maximum general depth? It is 4.5 kilometers. Even in the deeper part, you are not getting any kind of the coarse sediment that is getting. It is a really sediment star. Then how you get a sandstone shale, limestone deposit of several kilometers thick that is formed in the basin? It is not possible unless the basin is a subsiding one. There must be an active subsidence in the basin. And the subsidence in a basin, that basically is of two types. One is tectonic subsidence. Number two, sediment and water load subsidence. Water load. Sediment and water load subsidence. Those who are interested in the basin analysis, actually, I do not know whether you have idea. ONGC recruits geologists into two posts. One is a basin analyst, another is geologist. And I know many of my students, they got a job as a basin analyst, not as a geologist. So what ONGC expects out of them? That they will be analyzing a basin. What is analyzing a basin? That in the space and time, how the basin has evolved. Space and time, how the basin has evolved. How the temperature pressure regime in the basin that has changed over time. How the different kind of organic matter in the different temperature of regime that got cooked at different temperature at what time. And if at all it is the organic matter is cooked, has it generated hydrocarbon? If it generated hydrocarbon, how it is migration path, primary and secondary? And then how it got accumulated in a reservoir rock. Is there a reservoir rock that is present in the basin? All these, that is the work of a basin analyst. And in the process, what they do, basically, they do geohistory analysis. They do geohistory analysis. Geohistory analysis. I will not go into the geohistory analysis. Actually, there is a special course that is sequence stratigraphy and basin analysis. There I discuss all these things. There I will just introduce you what is a geohistory analysis. That's all. I draw a figure and that will tell you that what is a geohistory analysis.
lower part is not visible.
So what is the scale you mentioned here? 1 kilometer per 1,000 year and 3 kilometers.
1 kilometer per 1,000 year, that is in space, and 3 kilometer per 1,000 year, that is with respect to depth. Okay, is it drawn?
Yes, sir.
Okay. So what is shown here? 0 is the present. 0 is present. And I am going back up to 400 million. I am going back to 400 million. Okay. Now, if I go back to 400 million year when the basin started, and from that point, if I backtrack the history of the basin, and present day the basin depth is this. Present day possibly the basin depth is this. Okay. So if the present day basin depth is this, and I track back to 400 million year, and how the basin that is subsiding. So I am tracking back to different time period, and going back to the initiation of the basin, and tell to my authority that at this time the basin was in this condition, at this time the basin was in this condition. And out of this total, this was the tectonic contribution, this is the sediment and water load contribution. And the depth of the basin is this. So, do I expect that the organic matter mature at this depth if I take the geothermal gradient? So, average geothermal gradient is 28 degrees. So, if I reach to about 2 kilometer depth, I am reaching to about 60 degree temperature. And then if I go to 3.5 here, so there I get about 110 degree temperature. So this is the zone from 60 to 2. So any organic matter, if they present, it will create the oil, what we call the oil window. 60 to 120 degrees centigrade, that is the oil window where the organic matter creates the oil. Anyway, I am not going there. I just want you to know the importance of geohistory analysis. And then, if I know the age of different formations, and I can correlate that at this stage, what was the formation that was formed. So, from the geological record and all this data, our aim is to identify that from the beginning how the basin was formed and it got into subsidence. You got me? Is it clear or not clear?
Yes, sir.
Yes, sir.
So, this is what we call the basin analysis or geohistory analysis. Saying so, now this is more applied part that I have discussed. I will not go to the more theoretical. Because applied part is not part of this course. Applied part, for that there is a special course. Now, before, first people tried, because the plate tectonics, it came in 1960s. The concept of plate tectonics that came in 1960s. Before that people used to believe in the geosynclinal theory. I will discuss today the geosynclinal theory. That what was the geosynclinal theory and the basins related to the geosynclinal theory. What was the geosyncline? Because now, after the plate tectonics, people do not believe in the geosynclinal theory. Before the plate tectonics, people used to believe in the geosynclinal theory. What was basically identified at that time? That actually the Earth's surface, it is made up of craton and geosyncline. The Tethys Ocean was referred to as the Tethyan geosyncline. So the craton, and craton has two parts. One is shield, another is plateau. If you see the Indian peninsula, what is the shield area? Where you have very little scope for earthquake, which is a stabilized part of the plateau. Very little earthquake. And it is basically represented by granites, gneisses, and what are the platforms? Which are the peripheral part of the craton. Peripheral part of the craton, that is represented by orthoquartzite plus carbonate. Orthoquartzite and carbonate. That they say that is the product of the plateau. Shield has very little sediment cover. Shield has very little sediment cover. And between the cratons, there were geosynclines. There were geosynclines. And how was geosyncline? Please draw it, and after drawing, let me. The entire thing is called geosyncline. The entire thing is called geosyncline.
Sir, what is written on the extreme right side?
Eugeosyncline. 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 Eugeosyncline.
And the upper part too, sir. The upper part.
Genticline. Gmpicline. Genticline.
So please adjust the screen. Upper part is not visible.
So what is shown here, that between two cratons there were geosyncline. That was the earlier belief, because people used to believe that the tectonics on the earth are mostly vertical, not lateral. What is plate tectonics? That is, plate is forming in mid-oceanic ridge and in the subduction zone. So it is a lateral, it is a horizontal tectonics. What people used to believe? No, it was mainly by the vertical movement of the earth column. What is the isostatic concept? To understand the isostatic concept, what is the Pratt concept? What is the Airy concept? Those are the earth is in the form of some blocks. And these blocks, they are either in terms of their density or their different thickness, they are basically equilibrating with one another. And what kind of structure you expect if you consider the earth in form of some blocks? All you should expect that they are vertical techniques. So they used to believe in the vertical. The isostatic theory only give rise to the vertical techniques. Isostatic theory do not give any importance to the plate techniques. Have you ever thought about it? What is the problem between the isostatic theory? Isostatic पढ़ाया गया ना?
Yes, sir.
Plate tectonics भी पढ़ाया गया.
Yes, sir.
So what is the contradiction between these two? Have you ever thought about it? Who anyone has discussed? Who has discussed this? Any teacher has discussed this or not? Tell me.
No, sir.
Hello?
No, sir.
Why you people do not ask these things? These are basic problems of geology. तुम लोग को सोचना चाहिए ना. जब आइसोस्टेसिस पढ़ते हो, आइसोस्टेसिस क्या बोलते हैं? The earth is in the form of some blocks. सही में earth is in form of some blocks. तो plate tectonics operate करते हैं. How the plate tectonics operate? You have a plate which has a lateral movement, and you say that is a lithospheric plate that is moving on the Askam. A basic problem between the isostatic concept and the plate tectonics. If isostacy is right, I cannot say that the plate tectonics is also equally right. Now, when people used to believe in the isostatic theory and the vertical tectonics, during that time, this was the theory that the basins are formed as a geosyncline by means between the craters by means of vertical. All these theories got changed after the plate tectonics came. Now all the basins they are described in terms of plate tectonics. I will come back separately. If we believe in the isostacy and if we believe in the geosyncline, then this is the scenario. This is the scenario. A geosyncline has two parts. One is a myogeosyncline, another is the eugeosyncline, and separated by a gentle. Now, what is myogeosyncline? I am giving an example of myogeosyncline and eugeosyncline. Think of the Shivalik and think of the Himalaya, which is the Tethyan basin. The Shivalik is a myogeosyncline, whereas the main Himalaya, that is basically a product of a eugeosyncline. That is a simple example I am giving. If I describe it in terms of geosyncline, what people do not give importance. Now, what will be the product of the myogeosyncline? It will be a product of pluvio-lacustrine system. Pluvio-lacustrine. Pluvio-lacustrine. There will be river system. There will be the floodplain. And you can also get coal. You can also get coal. And popularly, these sediments are referred to as the molasses. Molasses. Molasse, please, these are the terms of the past when geosynclinal concepts were here. Now, molasse, please, is not used in plate tectonic terms. Molasse, please, these terms are tied up, tagged up with the geosynclinal concept, not with plate tectonics. Never use these terms in terms of plate tectonics. Now, if I come to eugeosyncline, it is a volcanosedimentary succession. Volcanosedimentary succession. There will be sediment, there will be volcanic succession. And they should be multi-deformed. They should be multi-deformed. And sometimes metamorphosed as well if they form a kind of orogeny, if they become a part of the orogeny. So that is what, if you go to Himalayan succession, what is Himalayan succession? It is a volcanosedimentary succession. Polydeformed, a little metamorphosis. And what is Shivalik? It is a pluvio-lacustrine sediment. So people say that yes, here we get, now people do not believe it. I again say that they do not believe it. But earlier people used to believe this. And that sediment which is formed in the eugeosyncline, those are called the fleece deposits. They are by turbidites. They are by different kinds of mass flows. And associated with volcanics, multi-deformed, metamorphosed. And that kind of thing that we call the fleece sediment. If you see, even people still now refer in the stratigraphy. If you see the stratigraphy, we refer some name, the Andaman fleece. It is named long back, Andaman fleece. Yes, what is Andaman fleece? That is nothing but a turbidite succession. Turbidite succession. Yes, the same type of succession, if you go to the Tethyan Himalaya, you get the turbidite succession. So this is actually the earlier geosynclinal concept. Okay, is there any question? Anything to be discussed? Yeah. Hello.
No, sir.
Okay. So here we end today. Tomorrow we will discuss that what happened after plate tectonic concept and what are the changes that we expect that is after the plate tectonic concept. Okay, thank you. It is already 11:30. You might have another question. Okay.
Thank you, sir.